Okay, so we're doing the subject of kinematics. We are interested in describing the motion of an object. Yep. And right now we'll describe objects as point objects. When is that possible? I'm sorry? So this, we can do this when the object is not spinning. Okay? So when every point on the object has the same velocity and the same acceleration at a given instant, then you can describe the object as a point object. Okay? You will learn that now to describe this motion, you need three variables, okay, in three dimensions. If the object was spinning, then you would need three additional variables. So we don't want to make things complicated. Okay? All right, so we want to describe this motion. You guys want to take an attempt at describing this motion? How would you describe this motion?
We should do a displacement vector?
Okay. So what do you think describing the motion would mean?
Where it's going, where it was.
So if you gave me the location of that object at every instant, then you've described the motion. You guys understand that? So you have given, if you give me that information, you'll have given me all the information there is to give about the motion. Okay? So mathematically, this is how it would be expressed. Okay, the location of this object, we're keeping it in three dimensions, x, y, z. And what I'm interested in is, where is it located at all times? So this is what I'm looking for. Okay. So if I have that information, if I have those three functions, then I know there's everything there is to know about the motion. Okay. Now in this chapter, okay, so what does the chapter title say? It's 1D motion. So the object will move in one dimension. Okay. So right now we'll keep things simple. We'll just describe one motion in one dimension. Okay. Either x as a function of position. Okay. So our object will be traveling along a straight line. So here's an example. Okay. So here's a straight road, and we are interested in describing the motion of this car as it moves back and forth on the car. Okay. So you give the position of the object with reference to a coordinate system. We'll give you the position of this object with reference to this point. That'll be the origin of the coordinate system. We'll call this the x-axis. Okay. So what this is showing you is there was a car a little while ago, there it is now, and so on, and then there it'll be in the future and so on. Okay. You see, this graph is a description of this motion. This graph is a complete description of the motion. When you are given a graph, you can figure out the function as the position as a function of time. Okay? Remember, what was the description of motion? You wanted to know where the object was located at all times. Okay, and this graph gives you that. See, at this time there is the object, at this time there is the object, at this time there is the object. There you go. Yeah, the complete description of motion. Okay, in a second you'll learn the following. Now, if you wanted to find the velocity of the object, let's say you wanted to find the velocity of the object at that time. How do you find the velocity of the object? I'm sorry? Yep, so you go to the graph, draw a tangent line, and the slope of the tangent line, is the velocity. Okay, so the slope of the tangent line is the velocity. And as somebody mentioned, it's the derivative of the position as with with respect to time. Okay. So, given this function, you can calculate the velocity as a function of time. And once you have the velocity, you can calculate the acceleration as a function of time, which is the derivative of the velocity. Or the second derivative of the position with respect to time. Okay. And right now, that's all we're interested in. Okay. So what we'll be interested in is somebody giving us this function, and from that, we will get the velocity as a function of time and acceleration as a function of time. Okay. All right. Now, if you make it to the big leagues, then you might be interested in the acceleration, time rate of change of acceleration, which is called a jerk. Okay. It really is called a jerk. Okay. And so on. Yeah. All right. So when somebody asks you to describe a motion, what is it that they're asking you? They're asking you to give the position as a function of time. Okay. All right. So we'll consider motion along a straight line. We will learn how to calculate velocities and acceleration. Okay. Then you will be interested in learning what causes acceleration. What will cause an object to accelerate?
Velocity?
Yeah, well, acceleration is change in velocity, but what causes acceleration? I'm sorry? Yeah, force will cause an acceleration. And so when you start applying forces, that part is called dynamics. Okay, then you're learning the causes of acceleration, and that subject will be dynamics. Right now, we're just interested in describing motion. Okay. So we consider motion of particles, point objects. What are we saying here now? What are we saying? Well, you have an extended object, except that it's not spinning. Okay. Every point on the object is moving with the same velocity and same acceleration, and you can treat it as a particle. Yeah. You already know what vectors and scalars are. Vectors are quantities that have magnitude and direction. Okay. Velocity, momentum, force, and all those guys are vectors. Speed is a scalar, and so on. Okay. Now, since right now we're keeping things simple and we're considering motion only in one dimension, your velocity can point either in that direction or that direction. Okay? So, in fact, in one dimension, all right, let me back up. In 3 dimensions, how many numbers do you need to specify a vector? 3. What are the 3 numbers needed for? I'm sorry? 1 for magnitude and 2 for direction. Okay. All right, and 1D, let's see. Your vector can either point this way or that way. So let's say this is 5 meters per second, and this is minus 7 meters per second. So in one dimension, there is the number for the magnitude, and the direction is just given by the sign. Okay, so you don't even need a number to give the direction. Okay, all right, so we'll remember that. All right, so let's make sense of this graph. So what is this doing? This is giving you the position of the object, x in meters, with reference to this origin. Okay, and the convention is positions to the right are positive, and these guys are negative coordinates. Okay, you could have done that as positive and this as negative. Both would be correct. Okay. So the convention here is this, these are positive position, those are negative position. And, as the object moves, time is flowing. Okay, so this is plotting the x coordinate as a function of time. At 10 seconds, it was at 50 meters. At 20 seconds, it was at 35 meters. 30 seconds, it was at the origin, and so on. Okay. What the slope of this line, what this is giving you is the average velocity between 0 and 10 seconds. That's what the slope of that line is. The average velocity between 0 and 50 seconds is the slope of that line. Okay. Now, the average velocity between 0 and 5 seconds would be the slope of that line. The average velocity between 0 and 2 seconds would be the slope of that line. And you see, in the limit this thing goes there, the slope of this tangent line is the average, is the velocity, the instantaneous velocity at 0 seconds. And that was the derivative that you learned in your calculus class. Okay? All right. So to describe motion, what do you have to do? You have to give the position of the object as a function of time. And you give the position of the object with reference to some coordinate system. Okay. So for instance, in your houses, you have addresses to your houses, and those addresses are with reference to some coordinate system. Okay. Every town will have an X and Y and coordinate system and the origin. So for in Daytona Beach, I guess ISB is the x-axis and Clyde Morris is the y-axis. Okay. Something like that. All right. So position is a location of the particle with respect to a coordinate system. A position time graph is a graphical representation of the motion. Okay. But graphs are good for pictures. But what we'll be interested in is this, okay? All right, so here's this armadillo walking. Okay, so what this graph is telling you is at 0 seconds, it's at minus 5 meters, okay? And let's see, you cannot draw the velocity in a diagram like this, okay? This graph can tell you when is the armadillo going the fastest? I mean, you look at this, you can't tell. But you look at this graph, you can tell when is the armadillo going the fastest. The slope is the steepest at 3 seconds. That's when it's going the fastest. Okay? And it's passing the origin at that point, and so on. Okay? So again, all right, now we'll just define some terms. Okay. The first one we'll define is displacement. Displacement is a vector. It's a vector that points, okay, so I'll do it in 2 dimensions. It's easier to understand there, and then we'll come back to 1 dimensions. Okay, so here's your starting point. You're going to point B. You traveled along that path. The displacement is this vector. Okay. So the displacement vector is a vector pointing from the starting point to the end point. What is the displacement for this path? The same. Okay. How about that? So the displacement is a 0 vector. Okay. That is different than the 0. Again, this is a vector. So in 3 dimensions, this would be 0i plus 0j plus 0k. Okay, so again, the displacement vector is a vector from the starting point to the end point. It's a vector. Okay. So for this path, the displacement vector was 0. How many different paths will have a displacement vector of 0? Infinite. Okay. So the displacement is like sort of an average quantity. Average quantities don't give you any details of the distribution. Okay. So go ahead.
What is the triple bar?
What is the what?
It's delta x.
Oh, that's is defined as.
Oh, that's cool.
No. Okay. All right, so everybody understands this. Now we'll come to one dimensions. Okay. In one dimensions, you're traveling in a straight line. Okay. So you start off here and end up there, that's your displacement. You start here, end up there, that's your displacement. Okay, let's say you start here, go there, and come back here. What is your displacement? This is your displacement. Okay? All right, again, what did we decide? In one dimensions, if the vector is pointing to the right, it's plus 0.5 meters. This would be negative 0.5 meters. The sign tells you the direction of the vectors. Yeah. Okay, this is just terminology. Trust me, you'll get used to it. So it might sound strange initially, but you'll get used to it. Okay, distance is a scalar. So distance is, so for this case, the displacement was this vector. Okay, so let me draw this displacement. The displacement was this vector. Okay, what is the length of that displacement? This is 1 meter, so 1 kilometer, so this is negative 0.75 kilometers. That was the displacement. What was the distance traveled during this journey? Yeah, 1.75 kilometers. Okay, and that's just a scalar quantity. It's just a magnitude. It doesn't have any direction. Yeah.
Why is it 1.75 if it goes forward and then?
Okay, 2.75 kilometers. Okay, so the distance traveled was 2.75 kilometers. Okay. All right. Let me remind you of vectors. Think about vectors. A is a vector. What is this guy? Okay. I'm sorry? Yeah, a scalar times a vector, which is a vector. Okay? So you multiply a scalar to a vector, you'll get a vector. Now, okay, so here's velocity. We'll look at it. Average velocity is defined as displacement vector, the displacement vector, divided by the time over which this displacement happens. Okay? Now let's look at it from a mathematical object point. This is a vector. Divided by a scalar, it gives you a vector. It's like a scalar multiplication of a vector. Okay, so this is a vector. You want to make sure that mathematically it makes sense. Okay, so vector times a scalar is a vector. What are the units of this? This is measured in meters. This is in seconds, meters per second. Okay. All right. In calculus, you learn that this is in the limit delta t going to 0, you take smaller and smaller intervals, then this becomes, that limit is called the derivative of the position with respect to time. Okay? And that's what we saw in the graph over here. See, there was the average velocity between 0 and 10 seconds. As you make this interval smaller and smaller, this line tends towards the tangent, and the slope of the tangent line was dx by dt. Okay? All right, so that is what you'll be mostly interested in. This is all for kids, okay? You guys are all grown up. So we will be mostly interested in instantaneous velocities and so on. So the instantaneous velocity is the slope of the tangent line at the point where you're finding the instantaneous velocity. Okay, so we'll also define the average speed. Average speed is the distance traveled divided by the time over which the distance was covered. All right, we'll do an example. So let's say you went to New York and came back. What was your average velocity?
That distance divided by the amount of time it took to get there.
Okay, so let me ask the question again. You went to New York and came back. What was your average velocity? 0. Average velocity was 0. You went to Tokyo and came back. Yeah, average velocity was 0. You went to Palm Coast and came back. Your average velocity was 0. Average distance is different in every case. Okay? All right. So average speed and average velocity are not related. It turns out that instantaneous speed and instantaneous velocity are related. Instantaneous speed is the magnitude of instantaneous velocity. Okay, so let's say when you're driving north on 95 at 80 miles an hour, your velocity vector is pointing north, magnitude of 80 miles per hour, and your instantaneous speed is 80 miles an hour. You are set to be accelerating when your velocity changes. Okay? So if between two instances your velocity changed, the change in velocity divided by the time over which that change happened is your acceleration. That's the average acceleration. Okay, what are the units? Velocity is meters per second. This is second. So the units would be meters per second squared. Okay? Again, we'll want to make sure acceleration is a vector, and this equation does tell you this is a vector, change in velocity is a vector, divided by a scalar is a vector. Okay? When you're speeding up, are you accelerating? When you're slowing down, are you accelerating? Yes. Okay.
Why would that be a yes?
I'm sorry?
Why would that be a yes? Like, when you're slowing down, why are you still accelerating?
Your velocity is changing. All right. So now what we'll do is, this is a good time to introduce this. (10 meters per second). Are you accelerating? Okay, we covered both bases, yes and no. Huh?
Yes, because you're changing direction.
Very good. Okay.
Vector change.
Yeah. So you are accelerating. Okay, so we will define two extreme cases of acceleration. Okay. Okay, so velocity, remember, is a vector. As long as the velocity vector changes, then you're accelerating. Okay. Here we drew, what is this example? In this example, only the magnitude of the velocity is changing. The direction is not changing. Okay. when the magnitude of the velocity changes, the acceleration is tangent to the path. Okay, so that's one extreme of acceleration. And here's the other example. Here we didn't change the direction. We only changed the magnitude. Here, what are we doing here? We're changing only the direction and not changing the magnitude. And you're accelerating. And the acceleration happens to be, at this instant, the acceleration happens to be in this direction. It's pointing towards the center of the circle. At this instant, it's pointing towards the center of the circle. Okay, so you can see that this acceleration is perpendicular to the path. Okay. When only the magnitude changes, the acceleration is tangential to the path. When only the direction changes, the acceleration is perpendicular to the path. Those are the two extreme cases. And of course, can you change the velocity? Can you change both its magnitude and direction? Yes, of course. Okay. Yeah, so you can do that an infinite number of ways. So then you would have acceleration components that are tangent to the path and that those are perpendicular to the path. Okay. What would be a good name for this guy? Okay, where is it pointing? Well, that's a good center. So you might have heard of centripetal acceleration. It's also called radial acceleration. Okay. All right, so when the acceleration is, and of course, this is important stuff. How do you give an object acceleration? You apply a force. Mr. Newton tells us that if an object has this acceleration, there must be this force acting on the object. Okay, so now you know that. Okay, so here's the sun. Here's the Earth going around the sun. The Earth is going at a constant speed of 30 kilometers per second. Okay, and we just learned that it is accelerating. The acceleration is pointing toward the center. So there must be a force acting on the Earth towards the center. And what is that force? There you go. All right. So now you've learned something. Every time you know an object is accelerating, you just go looking for the force that is causing it. Okay. All right. So acceleration is, the instantaneous value of the acceleration is dv by dt, which is d square x by dt square. Okay, so let's just do an example. All right, what have I given you? I've described a motion to you. Okay. Now what are you interested in? You're interested in calculating the velocity as a function of time. And help me out. That's a 3.
15t squared plus 12t plus 7.
Plus 7. Okay. All right, so here's what I want you to notice. If the position as a function of time is a polynomial of degree n, acceleration is a polynomial of degree n minus 2. Velocity is a polynomial of degree n minus 1. Okay. So this shows you, here's velocity as a function of time. This is a parabola, so velocity is a quadratic function of time, and the acceleration is a linear function of time. velocity was a quadratic function of time, and acceleration is a linear function of time. Okay? I'm sorry?
It went to white screen.
All right. Okay, I'll just show you one thing. Okay, so what we have done is we gave meaning to the slope of the tangent line here. Okay, so dx by dt was velocity. Okay. Now what we'll give you is a meaning for. So in calculus, okay, you had a function and one dimension function. Okay, there were a couple of things you were interested in about the function. So what you wanted to know was, at this point, how's the function changing? Is it increasing or decreasing, and how fast is it increasing? Okay, so the derivative gave you that information. If the derivative was positive, the function was increasing, and larger the derivative, greater the rate of increase. Okay. There was another thing that you were interested in. Okay. Oftentimes, you're also interested in the area under the curve. Okay. And you've learned that that area is given by the integral. Okay. So we'll show you examples of that. Okay. So for example, if you plot velocity versus time of an object, here's the velocity as a function of time. The area from t naught to t gives you the displacement of the object. That area is equal to the displacement. Mm-hmm. If you plot acceleration as a function of time, the area is the change in velocity. Okay? So depending on what it is that you plot, the area will have different meanings. You will see in a later chapter, if you draw force as a function of position, what does this mean? What that means is, let's say I'm pushing an object, and the force that I'm applying on the object depends on the position of the object. If the force is changing with position, okay, it turns out that this area will equal the work done on the object. Okay. The more work you've done, the faster the object will be moving. Okay. So again, so we are giving meaning to that area under the curve. Okay. Again, depending on what it is that you're plotting, that area will have different meaning. So when you plot velocity as a function of time, the area is the displacement. Okay, I'll just show you one little derivation. Okay. All right, so velocity at any instant is dx by dt. Okay. So here's an equation, and you've learned in your math classes that if you have an equation, you can do anything to one side of the equation as long as you do the same thing to the other side. Okay. So what we'll do is we'll integrate this side, integrate between t naught and t, t naught and t. Or again, and integrate the right hand side as well. This, you know, is the area under the curve. And the integration is, it's called an antiderivative. It's the inverse of the derivative. So when you integrate a perfect derivative, you just have this function. It's x t prime evaluated between the two limits. And that's that. So the displacement is the area under that curve. Okay. And you can do the similar things, and you will find that area under this curve is the change in velocity. Area under this curve is work. Well, you don't know this stuff yet, but that's what we're working towards. Okay. All right. So again, what we've done is shown you examples. When you learn about functions, you are interested in two things about the function: the rate of change of the function and the area under the curve. Okay. And we use that in kinematics, in physics, quite a bit. All right. Velocity is a vector. It has magnitude and direction. Acceleration is a vector. And how are the two related? I'm sorry?
Acceleration is the.
Time derivative with velocity. Okay, acceleration is time rate of change of velocity. All right, anyway, here's a physical example. I mean, here's a couple of things I want you to notice about this. So here's a car driving, and these are the velocity vectors. What is happening to the velocity vector? It's constant, so the acceleration is 0 for this guy. Okay. How about for this guy, the velocity vector? I'm sorry? So the magnitude is increasing. Okay. And the acceleration vector is pointing in the same, it's tangent to the path, as we said. When only the magnitude changes, the acceleration vector is tangent to the path, and the acceleration is tangent to the path. And what they're showing you is the acceleration is constant. Okay. In this case, it's constant. Okay. So here the magnitude of the velocity is decreasing and the acceleration is pointing in the opposite direction. And again, it's only the magnitude is changing, so the acceleration is still tangent to the path. Okay. So when you're slowing down, the velocity vector and the acceleration vector point in opposite direction. When you're speeding up, they point in the same direction. Okay. And if nothing about the velocity is changing, then your acceleration is 0. Okay. So this is velocity, a linear function of time. So velocity is a linear function of time. And if you take the derivative of this, you'll get a constant. So acceleration is constant. This acceleration corresponds to that. Here, the velocity, this is a parabola. The velocity is a quadratic function of time. Acceleration will be linear function of time. Okay. Here, the acceleration is constant. What is the acceleration here? 0. Not nothing, 0. Yeah. What is 1D motion? Motion along a straight line. Okay, that's what we're interested in. Here's the most common motion along a straight line. Okay, and this is constantly the acceleration is constant. Okay. So, for a freely falling object, okay, if you measure the position with respect to that as a function of time, the distance this object will travel will be a quadratic function of time. It will be a parabola. Yeah. Acceleration is constant, velocity is a linear function of time. Okay? So for constant accelerated motion, the velocity is a linear function of time, and the position is a quadratic function of time. Okay? So we will practice all stuff. I mean, right now, for now, we'll just keep things simple and we'll look at motion where the acceleration is constant. Okay. So you see, the position is a quadratic function of time. What this formula is telling you is, this is the displacement if you want, or you can bring this to the other side, and this is giving you the position as a function of time. The position of an object as a function of time is, so I'll write this x is equal to x naught plus v naught t plus 1/2 acceleration times time square. The position is a quadratic function of time. What this notation tells you is, okay, so let's put t equal to 0. T equal to 0 will make this term 0, this term 0. That's where the object is at time t equal to 0, and that's what that subscript 0 is about. Okay? If you take the derivative of this, you'll get, this will drop off, v naught, so let me do, vt would be v naught plus 1 plus at. Okay, so the velocity at time 0, this term would drop off, would equal that. So what this notation is this is where the object was at time 0, this was its velocity at time 0, and here's the acceleration of the object. Okay, that's what those terms are. So there, this gives you the position as a function of time for a constantly accelerated motion, for a motion that has constant acceleration. All right, the displacement can also be given in terms of the average velocity. As long as the acceleration is constant, average velocity is given as the final velocity plus initial velocity divided by 2. Only when the acceleration is constant can you get that. Okay. Here's velocity, a linear function of time. And this is giving you the velocity square as a function of displacement. This is giving you the velocity as a function of position. Okay, this is important. For instance, I don't know if you know this, but it's you need a longer runway to take off than to land. Okay, so a plane has to have a takeoff speed, and the runway had to better have a minimum length for you to take off. Okay, so this is how fast you would be going if you had that acceleration, and that was the distance over which you accelerated. You know that aircraft carriers don't have long enough runway. They don't have long enough runway to give you takeoff speed. So how do you solve that problem? I'm sorry? What? You use a slingshot. Okay. All right, so you give it an initial velocity using a slingshot. All right, this goes through the derivation. We won't worry about that. Okay, so here's the example. One example where you experience constant acceleration in everyday life. You try and maintain constant acceleration in your car for 4 seconds. I'll buy you a soda. I mean, good acceleration, not just. Okay, it's hard to maintain a constant acceleration. Okay. All right, so a freely falling object. So the acceleration is a vector pointing in this direction. Okay. What is the magnitude of this acceleration? The magnitude of this acceleration is 9.8 meters per second squared. Okay. Now let's make sure we understand this. Okay, so let's say if I draw the axis like this. what is the acceleration vector? And by the way, this is given a special symbol g, small g. Small g is 9.8 meters per second squared. Okay. Okay, so what is the acceleration vector? It's pointing in this direction. It's 0I minus gj. That's your acceleration vector with reference to this coordinate system. With reference to this coordinate system, your acceleration vector is 0I plus gj. You guys understanding this? All right. Let's say for some reason I chose to draw my axis like this. Your acceleration vector, the gravitational acceleration vector is always pointing down. It's gi plus 0j. Okay, so you guys understand that here is the acceleration vector, it's pointing always down. Depending on what is the coordinate system you choose, it'll have different components. Okay, that's all. Now, so here's the acceleration vector. Let's say here was your choice of coordinate system. This would be a very not so nice thing to do, but you could write it like that if you want to make life hard for yourself. All right, what this diagram shows you is, see, if you drop an object at t equal to 0 seconds, it's at 0 meters. You don't have to say anything, just point to the thing, and because we have to do it so many times. At 0 seconds, it's at 0 meters. Yeah. Okay, this is giving you average velocity. Anyway, don't worry about this. It's not a good diagram. All right.